I'm Akshita Gupta. Today, I will present our work OW-DETR Open World Detection Transformer. This is a joint work with Dr. Sanath from IIAI, Joseph from IIT Hyderabad, Professors Salman and Fahad from MBZ UAI, and Professor Mubarak Shah from UCF. Firstly, what is open world detection? Here, the task is to learn to detect unknown object instances and incrementally learn to classify them into their respective classes. For example, the input image contains both foreground labeled objects like person, bus, and background unlabeled objects like traffic light. The aim of detection model is to detect novel unseen objects and classify them as unknown along with learning labeled instances. And when the annotation for those unknown labels are introduced, the open world detector should be able to classify them into the respective classes without forgetting the labeled instances. These steps are continued till all the objects are labeled. Why do we even need open world setting? With the increasing data, it's getting impossible to label or semantically meaningful objects in an image. Whereas we strive to employ only certain fixed categories at a time for training the detector, and as the label space increases over the time, the same detector can be adapted to the new data. A recent work, ORE, introduced the open world detection setting. It is based on two-stage faster RCNN architecture, where the class-agnostic proposals from the first stage were employed for pseudo-labeling unknown objects, along with contrastive clustering of the latent space. Furthermore, an energy distribution-based unknown identifier was introduced to detect the unlabeled instances. However, ORE relies on an held-out validation set with weak supervision in its energy-based classifier for the unknowns. Moreover, during the contrastive clustering, it uses a single latent prototype, which is not sufficient to learn the diverse intra-class variations. Additionally, as the ORE approach is based on convolution architecture, it can't explicitly encode long-range dependencies. Briefly, OW-DETR is a fully end-to-end framework based on a deformable data pipeline. It is a multi-scale context-aware detection framework which aids in handling the scale issues. We propose a bottom-up attention-driven pseudo-labeling scheme along with novelty classifier and objectness branch for learning unknown object characteristics. While the novelty classifier enables distinguishing knowns from unknowns in a class-specific manner, the objectness branch aids in capturing characteristics of objects in a class-agnostic manner and enables knowledge transfer from known to unknown classes. An input image is passed through the self-supervised trained backbone. From the backbone, we extract the multi-scale features and the intermediate layer feature map is used in further training. The multi-scale features, along with a set of learnable object queries, are input to the deformable encoder-decoder, which contains multi-scale deformable attention modules. At the decoder output, the object queries are input to three different branches: box regression, novelty classification, and objectness. Meanwhile, intermediate feature maps from the backbone are utilized to obtain an attention map A, which is further used to learn the objectness score for a query. The queries with high score SO are selected as candidate instances and labeled as unknowns. The pseudo GT along with the GT known queries are treated as foreground objects and used to train the objectness branch FOPJ, while the regression branch FREG is used to predict the bounding boxes. A novelty classification branch FCLS classifies the queries into one of the many known classes and unknown class. Now I will present some qualitative results. Here we have attention feature maps along with their bounding box predictions visualized on the corresponding image. The bounding box in yellow indicates the known instances and in purple indicates unknown instances. We generally observe that the attention map activation tend to be higher for regions with foreground objects. Thus, it shows the benefits of the proposed attention-driven pseudo-labeling for unknown objects. These are a few example detection results which shows both known predictions and unknown predictions. Lastly, we compare our results qualitatively with ORE, and as we can see, the performance is improved both in terms of removing the false positives and predicting unknown instances. Here, for quantitative comparison, we employ U-recall, a known recall metric, for measuring the detection capability in detecting unknown objects. The unknown recall quantifies a model's ability to retrieve unknown instances. As we can see, in comparison to ORE, we achieve SOTA results with absolute gains ranging from 1.8% to 3.3% in terms of unknown recall. Thank you for listening to our presentation. The codes are open sourced at the shared link. Please do visit our poster.